And okay, yeah, thank you, Mark. Thanks for the welcome and thanks for the invitation. It's 8 o'clock here in the UK. If you hear screams, it's my daughter going to bed. But hopefully, my wife can muffle those screams in a friendly way. Anyway, I'm absolutely delighted to have the chance to talk. Looking forward to some good debate and questions as well later on. And I don't entirely know the backgrounds of everybody here, so forgive me if some of this seems easy. Forgive me if some of it seems difficult, but I'll try and kind of skirt a good balance through the talk. What I really want to get to is the final few slides where we talk about what BT is doing in terms of deploying this technology, because this technology is moving fast, and it's not any longer just a kind of physics experiment, but this is now commercializing for real. So really exciting time to talk about this. Cool. So forgive me just a couple of slides of context, but I work at BT, and the good old telcos in the past 30-40 years ago did a huge amount of research. I would say less so now, but still significant research is out there in the likes of BT and the equivalent in the US like AT&T and in Japan and other places in Europe. We're still proud of the research that we do. I would say it's, from a BT perspective, at least, it's more targeted now, in that we're looking for not inventing new kind of base technology, but how to exploit and commercialize it, what we can use to improve the network. But just a few figures there. We are really punching hard in terms of the number of patents that we're filing, and the impact that we're having on the innovation, and certainly within the UK and globally as well. And I normally work at this building here, which is about an hour out of London on the East Coast, near Ipswich, for those that know the UK. I don't really go there very much in the last 18 months, as we all know, although I was there today, talking to a very interesting company that I'll actually mention later, who are looking at satellite QKD, at a really profitable meeting. But I'm hoping that at some point in the next few months, life will return to some kind of normality, although I doubt it's ever going to be back to where it was. But anyway, that's an impressive kind of research place that certainly all my team will be in the lab there. Well, not now, but during the day. I think they're probably very happy that I actually don't come in, because I can't mess up their experiments. Just to position even more, we go back a long way at British Telecom, and we trace our kind of ancestry back to the mid 1800s. And we can cite some very interesting developments of technology along the way. Quite a few of them related to telecom transmission over fiber and related technologies there. 1984 was the year before I joined. Just talking to Mark, saying I actually joined in 85, which seems like generations ago. But yeah, the year before then, we did the first single mode fiber trial in the UK, between two towns in the UK, carrying 140 megabits per second. What's interesting to note is that over the last few years, we've been using the same fibers that we did those original trials now to carry single photon transmission. So kind of the whole thing's gone a full cycle, but it's now gone from classical to quantum communications, and it's taken 30 or so years to do that. But yeah, really exciting times. And it does feel that we're now sort of back to where we were in terms of this brand new technology just starting to emerge, and we're all wondering how to use it. That must have been how it felt like in the mid 80s when the first optical fibers were kind of provisioned. And for sure, I remember the first few years, apart from optical fiber being the means to get across continents under the sea because of its very low loss, we all kind of wondered how we would use the enormous bandwidth of optical fiber in terrestrial systems. We wondered, were telephone calls really going to be enough to fill this what seemingly unlimited optical fiber capacity? And then, sure enough, around the year 2000, we had the internet, and the rest is history. And optical fiber now is jam-packed full of data, and we're going through the same kind of discussions now. How do we boost the capacity of fiber? And I lead an optical research team that, okay, we do a lot of quantum, but our main day job is looking at how to innovate around the fiber that we have to squeeze more out of it, because finally in 2021 we're starting to hit optical fiber limits after all these years. So that's really exciting. Here's some more more recent developments, and you can see some of these are starting to hint at some of the quantum work that we've done, and I will for sure talk about these experiments later on. Just another one to out of interest to point out at the bottom right there, we over the last few months have been doing some serious trials on a new type of fiber. This is called hollow core fiber, and it is what it says. It's got a hollow core. So where you see the spectrum there in the center of the structure, that's where the light is guided. Outside you have a glass, but the glass is in a very interesting kind of format or structure, which keeps the light guided within this empty core. And that could well be of interest to quantum. And again, it's another question to come back to later, how the fiber evolution and the fiber world and the quantum world are colliding is a very interesting topic for debate later on. Okay, but let's get real. Let's talk about what the main subject today. This was quoted in Nature last year. We're seeing an exponential rise in the capability of computers, quantum computers. In this case, it's talking about photonic computers doing the calculations using photons. For example, boson sampling type computing. And they may be limited in what they can do, but nevertheless, there's an untold power coming from quantum computation, and I'm sure you've had talks on that over the last few months. Here's another kind of interesting fact that literally in the last few months, maybe year or two, we've seen the emergence of pretty large scale ambitions to build quantum networks. Now we know about the Chinese who have been leading the world on this for several years. Very impressive research going on down there with thousands of kilometers of QKD. So that's the target for all of us to try to emulate. But we're seeing other countries, nation states, very large companies, and continents, if you think of Europe, really motivating themselves to build big infrastructures. These are not just point-to-point quantum links. This is a national or international network. So this feels like a race. It feels like an arms race. It feels like an important thing in the 21st century to be doing as a country to make sure we're not left behind. And absolutely, quantum investment, as we'll see in the next slide, it's gone through the roof, billions and billions of dollars. In fact, before I come to that, just before I dig into the detail, for those that may be a bit hazy about what I mean by quantum, I just want to, point something out, and that is that the word is often used in different ways. And when we use it, we're probably thinking of something new in the way that we are capitalizing on features of quantum. For example, the fact that a particle can be in two places at once, that you can entangle two particles together so that the behavior of one impacts on the behavior of the other one, even though they're potentially thousands of kilometers away. Obviously, these are always been properties of quantum, but they've not been properties that we've been able to make use of until recently. If I look at my watch, which relies on semiconductor circuits that are basically quantum, they're not using these properties. They're using, if you like, quantum 1.0, that the properties of electrons going around atoms and in a quantized state. So that's quantum, and that's, if you like, quantum 1.0. What we mean now when we're talking about this new wave of quantum is really harnessing these other properties, the properties of position or state probability, where you can have two or more states at the same time. How do you harness that? Or the fact that you can, as I say, you can have particles entangled so that you can somehow have a link between them, even though they're not close to each other. And what I'm going to be talking about in the rest of this talk is how to harness those extended properties. And I think what's changed in the last 20 years is our technology. So we've always known about these properties. It's just the technology to be able to control them is something that's moved massively in the last 20 years. And as I was saying earlier, that there is a huge investment going on globally. And it's in a wide range of areas. And I just want to go through these because it's not just about, for me at BT, it's not just about quantum communications. In fact, we're doing different levels of research in all of these bullet points on the left. In the UK, who have been, I think, very proactive and forward-looking in terms of investment, there's been quantum hubs focused on all of these applications for the last 8 or more years. And little small groups of universities and industrial players have focused around all of these different topics, and have really pushed hard on converting research in these areas, these different quantum areas, into some purposeful innovation and exploitation. And for BT, we've been particularly interested in the first, fourth, and fifth. So I'll talk about those a little bit. So firstly, quantum clocks and timing. We currently have several projects, both internally and within the UK and within Europe, developing the science of quantum clocks, but also the use cases and the applications. And the potential here is to build a clock that is incredibly accurate, and I would say probably more accurate than any applications that I can think that would make use of that, other than, I guess, big science experiments. But for communications users, clearly we have a need for a synchronized, well-timed network. Okay, the network as a whole, that I'm including 5G, I'm including fiber communications, I'm including satellite, global, international comms, relies on well-defined clocks. And clearly, quantum clocks and atomic clocks have the potential for giving us just the most accurate clocks in the universe, clocks that could be accurate to within a second over billions of years. And that's maybe even more accurate than we could even envisage requiring in communications networks. Nevertheless, we expect to see spin-offs from this technology. And at the moment, our research activities focused on some of those use cases that could make use of very accurate timing that's better than the current timing available from GPS or from the current method of distributing clocks in the network. We have spent a bit of time looking at quantum imaging and quantum sensing, and in fact we've been looking at quantum gravity sensors to explore what we can see under the ground. So we've done some very early trials looking at using quantum gravity to see if we can find our cables. Sounds like we've lost them. So we know where our cables are roughly, but to be able to pinpoint them and to be able to identify things like flooding or damage or maybe mud ingress, all the kinds of things that will reduce the reliability of our network. We have been wondering and exploring the capability of quantum to do very, very fine, accurate sensing. So that's, we're looking for applications of quantum in our own environment. But I would say it's really the last two that have captured our imagination as a company. And the first one, quantum computing, is obviously the really big kind of sexy application that the whole world is captures their imagination most. And for us, there's really two kind of ambitions here. The first is, could quantum computers help BT to run our networks better? So could we use quantum computing to optimize the big problems that we have as a company, such as optimization of our network, where to deploy resources on a second by second basis to keep that cost minimal. So there are big optimization stroke logistics type problems that the big telecom networks find. A telecom network is just about the most complex thing that you could imagine, and so to having a quantum computer to optimize it must be a good thing. The other avenue to explore here, though, is whether a large carrier like BT could actually sell quantum compute as a service. And there, the use case would be, if you want some quantum compute resource, you're unlikely to buy a quantum computer, probably too expensive. Also, you might be reluctant to get that resource from a company you've never heard of. All of the issues of trust come in. So this might be an avenue that BT can explore in terms of selling secure access to quantum compute resources. But I've left that, for us, the most interesting one till last is clearly using quantum for communications. And here, the main objective at the moment is to see whether quantum comms can significantly improve the security of our communications networks. And we would want to do that for a range of reasons. We want to do that for our own data to make sure our networks are controlled securely so no one can hack into them and bring our networks down. And secondly, we would want to use secure comms to sell to customers so that they can be guaranteed that they have complete security of the data that they carry over BT's networks. And you might ask, well, what's wrong with the current situation? Why do we need to bring quantum into the picture at all? And this slide here, and you may know this already, so just to go through this quickly, and it's a little bit complicated, okay? The way cryptography works currently is in a kind of two ways. The first thing you do is take some data and encrypt it with a key, and you need to make sure that that key is at the other end. So say if I'm sending some data to Mark, I would encrypt the data with a key, send it to Mark, and he needs the same key to unlock the data. A symmetric encryption. But then that begs the question, well, how did I get that key to Mark in the first place? And that's the second phase. And there, the question is a bit deeper, because what is used at the moment is something called public key cryptography. In other words, I will use a key pair that Mark will have a public and a private key. I would look at Mark's public key. I would use that to send him this symmetric key. In the knowledge that no one can unpick that, no one can hack into that unless they have the same private key that Mark's keeping private. Having said that, there's clearly a relationship between the public and private key. So this public key crypto is built into our Ethernet and our communication systems as the de facto means of distributing symmetric keys. If and when someone finds a very easy way to discover the private key from the public key, we're in trouble. It turns out that is a very, very complex, hard, difficult problem for standard computers. That's billions of years of calculations. And it's based on various hard problems, the simplest to understand of which is to factorize big numbers. And so that's great. We have a system which is very, very hard to hack. Except that quantum computers are coming and they will find that problem much, much easier than classical computers. And quantum computers with an algorithm that was discovered or invented by Peter Shaw many years ago work on a different principle, and they have a method to find the factors of large numbers, for example, by kind of simultaneously looking at all of the solutions rather than linearly working their way through like a classical computer would have to do. They do this using this quantum Fourier transform. I'm not going to go through this. This is a whole talk in itself. Fascinating subject and absolutely brilliant work from Peter Shaw. And it's an algorithm just waiting to be run. And what we need, of course, is a quantum computer that is big enough to run this at scale. And then we have obviously a major issue because all of the world's cryptography that's based on public key crypto is going to be at risk at that point. Okay, so the question is when, and this is the kind of $1 million question. If I knew when this problem was going to hit, I'd probably be very rich because I'd know where to invest. So here you can see me really essentially hedging my bets. What I'm plotting there is the years along the x-axis, and I'm predicting the number of qubits that I'm likely to need, and these are proper 4 qubits, proper logical qubits. I'm probably going to need a lot more actual qubits than that because of something called error correction. But just focusing on this curve for a minute, the yellow line suggests, well, when I'm passing that line, I've got a problem. And these various lines that are growing are really me basing my model on different assumptions as to how quickly the world is going to develop quantum computers. So it could be anywhere in between the next 5 and the next 20 years, depending on whether you're bullish or whether you're conservative about how quickly you think quantum computers are going to grow. So I'm not really answering the question, but what I would say is just the amount of investment and activity, almost on a weekly basis, you hear new reports of quantum computers. That you know, the global effort is so vast that this will happen. So long as this problem is just an industrial challenge, and I think it is. I don't think there's any kind of physics barriers stopping this. It's essentially just, can you build the technology required at scale? So what does that mean then? Okay, so we have a situation where our cryptography systems are going to be undermined at some point, and they are the basis of pretty much everything that we do online and as companies. And so we need some kind of answer to that. And what we've been developing as a community is fighting this quantum computer threat with another quantum technique called quantum communications, using quantum key distribution. And I just want to say in brackets, really, quantum computers could be and will be a very big force for good. You know, there's many problems they're going to be incredibly useful for, and it's extremely exciting. It's just they have this other feature of being able to hack into or be able to crack public crypto algorithms. So, and I'm not going to do very much in the way of physics. You probably had talks that have done this already, but I just want to point out 1 or 2 things. How QKD works, that the whole objective here is that I now have a different method of getting that key to Mark than I had before. Instead of me using a public crypto algorithm, I'm now going to send the key in a completely different way. I'm going to send it on single photons of light. So there's no maths here. This is really physics rather than maths in terms of the rationale behind the solution. So I'm sending, you can see there a picture of what single photons, each of which are carrying potential key material. Encoded in different ways. It could be the polarization, it could be the phase, it could be the position of the photons. There's different properties of photons you can use, but essentially you're manipulating them and sending those photons one at a time to the other end. Some will go missing, some will be attenuated by the fiber, and then they reach the other side and they will be detected. There's then a conversation to just to check which ones were received, and out of that a key emerges, and this key grows and grows continually, and it could be growing at hundreds of thousands of keys per second depending on the distance. So very fruitful way of generating random keys over a long period. The interesting question is what makes that so difficult for a hacker? What makes it impossible for a hacker to intercept? And they're just the 2 things I want to point out. Firstly, if she steals one of those red blobs, one of those photons, then it doesn't get through, and so it can't be used to form a key. If she tries to do something more subtle, and this is really hard, by the way, and just observe one of those photons as it flies past, or maybe detect it, measure it, and pop it back in, or put another one back in with the same characteristics, that's impossible as well, because the very nature of looking at a photon changes it. It's the shredding a cat Again, all of these photons could be imagined as shredding a cat in a box with the lid closed. And Eve, when she's hacking, is opening that box, and just the act of opening it and looking at the photon changes it. And that's detectable. Okay, so we have here potentially, as long as this is built properly, an unhackable means to transmit data, to transmit secret keys, and then those keys are then used in the way that they were before to encrypt data classically. Okay, so this is only distributing keys. It's only one half of the process. Once you have the key, once I have the key at my end and at Mark's end, I then use that key to encrypt the data symmetrically like I did before. And BT has really been very interested in this in the last 8 or more years. And these are the things we've done. And I'm going to go into some detail about these things. So we've wanted to turn QKD into something that we could exploit by seeing how it integrates into our mainstream transmission. At the same time, we've been working with customers to see what they would want to use from this, and how they might benefit from this. And I would say that over the last 8 years, there's been an interest that's been growing slowly, but in the last few months, I am probably talking to customers very much like I am here tonight every week. There will be customers of BT coming saying, we've heard a lot about quantum, can you tell us about it? So that the interest has grown dramatically in the last few months. We've been building a wide range of demonstrators, and I'm going to talk about some of these. The purpose for us is to see how to integrate quantum and classical so that we can provide a fiber that has the complete solution on it, carrying QKD keys as well as classical communications. And I'll talk about the various demonstrations that we've done. We're working on business cases because clearly we want to sell this and we need to work out how much we can sell it for. And some very exciting news in the last 2 months, we've really developed 2 relationships. One with a company called Arkit, and I have a slide on Arkit, who are building the first commercial satellite cluster to do satellite QKD globally. And then secondly, a close relationship with Toshiba, who are doing the same thing for terrestrial QKD over fiber. Two very exciting relationships, as well as all the other kinds of things that are maybe less glamorous but just as important, like doing penetration testing, assurance, standardization, management of the keys, and all of those good things. So very quick kind of review, and then I want to get to where we are now. So I'm just going back 7 years. This was our first contact with QKD. Well, actually, BT worked on QKD back in the 90s and developed some of the very early patents, but then we left it for a while because clearly it wasn't time. Back in 2014, we got back involved, and this was the first field trial we did with Toshiba and Adva. And what's notable about this is you can see the Toshiba QKD boxes at the bottom, Alice and Bob. Alice is sending single photons modulated with keys. Bob is detecting them with his single photon detectors. And obviously there's some details here in the implementation. Adva are a German company who BT used to provide Ethernet comms for our customers. And we really thought it was essential to bring these 2 together. We don't just want to distribute keys, we want to use them to encrypt our data comms. So this was the first time I think that this has happened. We had a potentially fully commercial solution on our hands. We went further, and 4 years ago, we had the culmination of a very big government-funded project that was led by one of those communications hubs that I talked about a few slides ago. This is obviously the Quantum Comms Hub, led from York University, but with other universities involved, notably Cambridge, who worked with us and with Adva again, but at this time also working with ID Quantique, another very notable and impressive QKD vendor. And here we built a longer QKD link over installed BT fiber, going through a range of actual BT nodes, BT buildings. We did fully trusted node implementation here. So essentially these are separate QKD links 1, 2, 3, 4 completely separate links with key kind of regeneration, if you like, at those trusted nodes. At the same time, this link carries now not just 10 gigabits, but hundreds of gigabits of data. And it's been running for the last 3 or 4 years. And we've used this to build our understanding and expertise on how you would do this for real. So this, is no longer physics. It's all about how can you convert this into something that we could use in our network. And I would just say that's not trivial. If you think that the job's done once you've built your QKD box, that's not the case. The integration, the implementation of a solution on a real live network, it is years of work, years of learning of how to do it. I'm just going to have a sup of water, and then I just want to talk about something really exciting. And this is a company called Arkit, who actually I've spent the whole of today with, and they are hugely innovative. Now, we've seen satellite-based quantum systems. The Chinese were the first to launch the Mikius satellite. I think I'm pronouncing that right. And we have now an existence theorem that has proven that single photons can be sent from satellites or detected by satellites, and they give you the opportunity to distribute secret keys now from a satellite to a point on the planet. Then the satellite is then flying around. In the case of Arkit, we're thinking of low Earth orbit, but then taking the keys that have been disseminated and redistributing them to another point on the planet. And as you see in the picture there, essentially gives us a means to do key distribution planet-wide. Now, I think you can see the real benefits of that. What I've talked about already up to now is fiber-based distribution. If we can add space distribution on top of that, then we have a global solution. We can do the very large intercontinental or national distribution using satellite, and then we can break down to more metro regional distribution over fiber. Then we've solved most of the problem, except maybe for that very last mile, which I'm going to talk about in a minute. So thrilled to talk about these guys. Very exciting. BT has signed an exclusive deal with Arkit to be a wholesaler of satellite keys in the UK. And you can Google that and find out more about it. But you'll see a lot more about these guys when they start to launch their satellites in a couple of years' time. I want to kind of go from the global key distribution from satellite to something much, much smaller, because we have to crack the short distance problem as well. It's no good getting your keys to within a mile of where you need them. That hasn't really solved the problem at all. You have to get them to exactly where you need them, because people will attack the most vulnerable point in a link. And here we built a demonstrator with a company called NCC. Last year, during COVID delayed, but didn't stop us doing this. And here we have 2 buildings in Bristol in the UK, and we've connected them together using QKD, using Toshiba equipment. That might sound fairly trivial, but there's something novel about this in terms of how we've used commercial technology to make this into a product that we could sell again and again. And that is, we have used BT fiber products, and we've developed them in a way that will just carry QKD without having to change any specifications or anything. And that sounds a bit confusing. I maybe can explain it on this slide here. This product is it's not a dark fiber, but you can buy from OpenReach in the UK. You can buy a link between 2 buildings which has a box on the end, and this box gives you access to wavelengths, either 8 or 16 wavelengths, for you to use however you want. And you don't just buy the fiber, you buy the fiber with the boxes. And this is called Filter Connect. It's a special product that's intended for anyone to use to do Ethernet connections. So if you want to connect up a business in the UK, they might have a Filter Connect solution which would allow them to have multiple wavelengths carrying 10 or 100 gigabits. But you can use these wavelengths also to carry single photons, and that's what we did. So this solution, we make use of some of those 8 or 16 channels to carry Ethernet and to carry classical waves, but we use one of them to carry single photons. And so by cleverly putting the right things on the end, we've turned an open reach basic fiber product into something that does way more than they expected. So this is now carrying ultra secure QKD plus encrypted Ethernet data. Now, the other thing to say is it's really complex, and the QKD bit resides down here in the light blue. But look at all this other stuff that's needed to make this work. All of the management, all of the data, the classical data communications, the firewalls that allow you to make use of those keys within the building, because the keys will be probably based in the communications room at the kind of output of the building. So you've still got a whole job to do to disseminate that information, those keys within the building. So, just having the physics working, I was going to say is the easy bit. I mean, it's clearly not, but it's not the only thing you need to do to make this work. And so just want to spend the last couple of minutes really looking at what does that mean? Because I've talked about satellite. I've talked about access to businesses. What about the rest of it? I've kind of hinted that there's going to be a kind of balance between satellite key distribution and terrestrial fiber distribution, and quite where that balance fits in, is it more on the satellite or the fiber side, is a very interesting question. But what I see is at some point we're going to need a network. Now, what do I mean? I mean that access links are point-to-point links. I connect a building like a business, a factory or a company into a BT network by a point-to-point link. At the other end of the scale, I might connect London and Tokyo or London and New York with a satellite in a kind of point-to-point satellite link. But in the middle, I've now got the potential for hundreds or thousands of customers all wanting secure data coming into a network. I'm not going to build thousands of separate links. I'm going to build a network that aggregates all of these keys together and carries a single metro or national key around my country. And all of the people using secure networks will have a share in that. That's what networks do. Networks aggregate, very much like small roads that you drive on filter into bigger roads, which filter into motorways. A network is based on big motorways around the country, smaller roads in a metro region, and then very tiny access roads that take you to where you live. Exactly the same with networking. And it's this this middle bit that is the real challenge at the moment. So I can do the point-to-point access. I think we know how to do the satellites. Very hard, but I can see a way to do it. The challenge now is going to be as QKD develops from point-to-point into a network. And the challenges are things like, how do I do key management? When I've now got keys going all over the place. I've got keys going from end customers to end other customers. You have to make sure they don't get confused, etc. So lots of very interesting networking challenges around that. And then just a kind of a map of how that might look like. You could imagine some satellite QKD stations around the country. You can imagine a big national network linking those with the major cities, and then you could imagine a metro network taking those quantum links to individual points where they're needed. And so I've had 40 minutes, and want some time for questions. So what have I been talking about? I've really tried to be positive because there's some, it's extremely good news over the last year or two that QKD has moved from physics to now something that we could commercialize. The physics carries on, and I'm still seeing some brilliant work going on around the labs around the world, making sure that the QKD doesn't stop, but it improves in terms of key rate, in terms of distances, in terms of security, and there's many other directions that QKD is taking. But at the same time, you don't want to wait until that's finished before you start to commercialize. So BT is intercepting the research development and trying to tap in here and here and here and say, we'll have that, and we'll commercialize it. And then as you move on, we'll take that and we'll commercialize that. That's really where BT is at. It's only one part of the overall solution. You've got to build in all of these other bits in terms of managing keys, managing firewalls, integrating QKD with transmission. And that's what I've been trying to hint at over this talk. And I think there's a real opportunity for the likes of BT and others to take a lead, because we're good at networks. We know how to build networks, and it's just another network. It happens to be carrying keys, but apart from that, it looks very similar to the things that we know how to do. So I expect to see in the next few years the big carriers taking a lead in terms of building out these quantum networks. What I haven't talked about much is the quantum internet, and that's not a topic for this talk, and I don't want to get those confused. So the ultimate kind of provisioning of quantum entanglement to connect up quantum computers is still a very, very long way off, and I haven't really touched on that. I think that's a separate subject. But to finish on the good news, we're seeing customers wanting this. We're seeing QKD ready finally to meet the needs of customers in a real commercial situation, both over fiber and over satellite. So thanks for listening, and I'm really looking forward to some good questions. So please shout out. Thank you, Mark.
Super. Thank you, Andrew. That was fantastic. There's already many questions in the comments here. So the first from Barry Bird, can you be more specific about the key being refreshed constantly?
Yeah, so I wasn't really very clear about that. But within so we could go back to this slide. This one here. Yeah, I haven't drawn this, but if you look at with that key at the bottom there on the left, you can see kind of red string of ones and zeros. So at the heart of this is something called a quantum random number generator. It doesn't have to be quantum, but it should be. So this is something that spews out complete strings of ones and zeros. Mark's an expert on this, and it's just doing it constantly. And these are very high entropy, guaranteed random ones and zeros. And those get turned into a distributed key that gets impressed one key at a time, or one bit at a time, on these photons. Many of them will disappear, many of them will get attenuated, but some of them will get through to the other end. And so that initial source of randomness, some of it will have communicated through to the other end, but it will just go continually. So the keys are appearing at both ends will just keep growing and growing. And actually, you probably can't use them all. So what you have to do then is think, well, how long do I want to store these keys before I throw them away? Because storing them is a liability as well. So what you find then is key buffers, where you generate keys, you store them for a while, but then you have more coming, so you throw them away. And that's an important part of the security as well. But I hope that kind of answers the question.
Yes. The next question, would you be able to point to implementation details of Toshiba BT?
Yeah, well, I mean, I'm not going to talk about Toshiba's implementation. Obviously, that's up to them, and that's their technology. Generally, these technologies use protocols such as BB84. Others will use something like COW, coherent one-way, but BB84, I think, well known as the Toshiba solution. So you can go and Google BB84 and see how that works. But essentially, the operation is around making two basis states. So you can generate a photon using either something like a horizontal vertical state, or you can do it using something that's 45 degrees to that. So in other words, I can send, as you can see in my hand, you can send a 0, let's say polarized this way, and a 1 polarized this way, or you can send a 0 polarized this way and a 1 polarized this way. Now this basis state you can change randomly. Okay, you use your random numbers to generate the keys, but also use it to generate your basis state. And at the other end, if Bob uses a different basis state to measure, he'll get the wrong answer. So Alice and Bob have to use the same way of preparing and measuring, otherwise they'll get confusing results. And so what happens after the keys have been sent is Bob and Alice get together, and they agree, they just compare notes. And Alice says to Bob, well, how did you measure this key? Bob says, well, I measured it like this. And Alice says, oh, great, that's how I sent it. Let's keep that one. So yeah, that's how BB84 works in a hand waving way, and that would be what Toshiba are doing in their box.
Super. In the case of filter connect, do you use polarization or another property of photons?
That's a good question. Let's go to that. So when I say WDM, that stands for wavelength division multiplexing, and these little boxes here separate out the C band, so the optical spectrum in fiber, which is in around 1.5 to 1.55 microns. It's like a few tens of nanometers in that region. It's very broad. Actually, it doesn't sound broad, but actually you can carry 20, 30, or 40 terabits of information per second over this band, and that's too much for one wavelength. And so what this filter does is it wavelength separates, using like a grating essentially, separates these wavelengths into, in this case, 8 or 16. And so you have essentially wavelength channels. So you stick your lasers in the middle of these channels, and that generates 8 or 16 times as much information as if you use one channel.
Right.
And that WDM is the way that you do classical comms. Okay, so our and other national networks are based around WDM, and actually normally more than 16 channels. So BT's WDM network has got 100 channels per fiber, all in the C band and all separated by a fraction of a nanometer.
In BT's quantum resistant networking plans, do you see any place where the software-based post-quantum encryption approaches may also be used?
Yeah, I think the two are going to have to work together. We're following with great interest what's happening in the NIST competition. I would say that, because BT is fiber rich, we are keen to use a solution which exploits our fiber. There's going to be situations where fiber is overkill. On the other hand, I would expect the QKD technology to start to impregnate standard telecoms technology. So it would not surprise me in a few years to find that you can buy a 100 gigabit transponder with some quantum built into it. And that maybe at a premium. So, I might say, okay, this wavelength I want to be quantum protected. This one I don't need to be. So I might pay a bit more for this one. But I would expect our basic telecoms fiber networks to have quantum security just as part of them. But on the other hand, you're not going to have a fiber coming to your phone. I don't think. You won't have fiber going to your smart meters in your garage or whatever. So absolutely places where you need another form of encryption. And I expect some of these NIST post-quantum algorithms to help with QKD as well. So we haven't talked about authentication, but there's a situation where you're authenticating your Alice and Bob may well rely on a post-quantum algorithm.
Thanks. I know that Sid Lang has had his hand raised for a little while. Sid, do you want to ask your question?
Hi, can you guys hear me?
Yeah, hi Sid, how are you?
Hi, I'm doing well. How are you?
Great, thank you.
I have two questions. One on your fiber optics based QKD delivery, and other is more satellite. So I think the fiber optics is still the way to go, because my question is, you can transmit a very, very, like you said, in your multiple wavelength bandwidth, you can select which wavelength you want. But how you guys think about implementing a spectroscopic based techniques to add another level of security, especially with exotic materials, which can only be implemented at your Alice and Bob locations? And because way I think about it is, like, as you probably know better than I do, in all these fiber optics, there is a loss. You lost photons, you lost signals. And somebody can always put based on the knowledge we have, a beam splitter on your fiber optic and just bypass it. And then maybe they won't be able to hack it, but they will be able to decode it based on the beam splitter, and you wouldn't know, because it will be under what is the expected loss. Have you guys thought about that? And how do you overcome it? You see what I'm saying?
Yeah, I do. There's kind of two aspects to this. Let me answer them separately. The first aspect is the beam splitter. If a beam splitter is used on a single photon, the single photon doesn't split in two. You can't have half. So the guy that's got the beam splitter either steals the photon or he doesn't. If he steals the photon, it doesn't get through, so we just don't use it. So he can steal everything he likes. I mean, he can steal everything, in which case obviously the system doesn't work. But the whole point of cryptography is to try to protect against people when you don't know they're there. So a beam splitter on a single photon system is useless. It's not going to work. But yeah, go on.
Sorry, I'm sorry, let me go ahead. I mean, he's stealing it, but he also has a similar network. So let's say I detect a single photon of 1550 nanometers in, say, vertical polarized, and I have a laser that will just send another position through a different way, so that he is like reactionary to the detection and
yeah. So if he tries to do something like replace that photon with another one to defeat the system or to get in there. So what another thing I didn't really explain about the way this works, but Alice and Bob reserve a percentage of photons just to check to see if anyone's fiddling around with the system. Okay. So and they do that at random. So it's not predictable. So Alice and Bob will say, okay, let's just use this photon to see if anyone's changed something. And so if someone tries to fiddle around, a sort of man in the middle attack is what it's called. That they can pick that up as well. We do kind of try and brainstorm all of the possible ways that Eve can do something dodgy. Like one of the things that really concerns us is what if they shine a laser? Just like you say, what if they shine a laser at our detector and try and kind of work out what the state of the detector is just by reflecting a laser off it, and they have inbuilt into these boxes, they have ways of detecting that as well. The other aspect of your question, though, I think was really interesting, was about using other means to do security, such as clever spectroscopy. Now, I'm really interested in other means to do fiber-based security. What I would say is that they're not as developed yet as QKD. I'm still not entirely sure that they are provably secure in the way that QKD is, but we are tracking those as well, for sure.
Okay, yeah, because I would not be saying it as a replacement, but like on the end-to-end user type. Yeah, basically, definitely. So because we are adding an additional level of complexity to it, and something as you can talk about is as a filter. So it can be a specialized materials filter that you would only have a spectroscopic information of what wavelength is going to put out on. So you're looking at like more like a fluorescence or some type of different scattering at the end.
Yeah, I mean, I like anything like that is interesting, but what I would say is it has to have an application, and I would say that cost-effective endpoint applications where QKD might be over the top, that's the place to go. So if you have a solution that can do something that maybe not absolutely the same rigor of security that QKD offers, but still pretty good, but is very cost effective for maybe at the end of a fiber into someone's home, I think that would be really exciting.
Yeah. And my second question was about the satellite. I mean, that is very interesting that people are thinking about low Earth orbit, but there is a big issue. I don't know if anybody has thought about it, or is that low Earth orbit has high concentrations of atomic oxygen. Atomic oxygen is very, very reactive. So all I have to do is fly a drone with a broadband fuel in it. So as long as, what I mean by broadband fuel is, I have a fuel, I will just release that fuel with the drone in low Earth orbit. So it's going to react and form a bunch of exotic chemicals that will absorb a very broad range. So it doesn't stop the communication, but just blocks it. How would you get around that?
I'm sorry to interrupt Sid, but no drone can actually fly in the LEO orbit. And the LEO satellites that actually do fly, they do contain enough propellant to make that happen, but that doesn't work. So I think this is irrelevant at the moment.
Yeah, I haven't thought about that, Sid. It sounds pretty dramatic to me. I mean, most of what we're kind of discussing here is surreptitious hacking, where we don't know that it's going on. And what you're saying there, that it doesn't do that. You still have the same situation with single photons, but of course, you stopping the thing working completely. You can do it with fiber just by cutting the fiber. That's a different kind of problem. And there you just need to, what you need to do is organize some kind of resilience. So I think with satellites, you need more than one. You need a cluster just to make sure that if for whatever reason one satellite isn't working, could be weather or something, you can rely on another one over here to give you that kind of resilience.
Okay.
Good.
Thank you.
Good questions. Thank you, Sid. I see that Raja Gopal has had his hand up for a while.
Yeah, hi, Andrew. This is Raja
Hiya.
from Middlesex University, Kathy's friend.
Hi, I recognize the name. How are you?
Good. How are you?
Good.
So I didn't quite get an answer to my question about the filter connect. You're still using photons there to do QKD, or are you doing some other means? And if so, are you using polarization or something else?
Yeah, so I didn't explain this very well, did I? This filter connect is a fiber, pure dark fiber. At the ends, it's got a box, and that box is essentially just a grating. The grating divides the C-band into 16 channels.
Okay.
Those channels, and that's it. So if you want to send whatever you want down that fiber, you have to pick one of those 16 channels. In fact, you can pick all of them. What we're doing with this solution for NCC is we're choosing one of those channels and we're sending single photons. We're using the other channels to send classical information. In fact, some of those channels will be used for the discussion channel between Alice and Bob, and then the other channels will be used for data. So one QKD, and you can pick whichever one you want. For QKD, and then you can use the others for your data. Does that make sense? So there's nothing to do with polarization. Okay, it's just wavelength. The polarization can be anything. They're completely polarization insensitive.
Okay, great. And the other different question I had was kind of an addition to Doug Fink's question. Could you use post-quantum cryptography for securing the trusted nodes, because trusted nodes are sort of a weak point in your network, right? I mean, they're can you somehow use PQC based things for security of these things?
I hadn't really thought about that. I think the problem with the trusted node is the keys are now in the clear. At some point in that node, there will be a key that you can encrypt it again to get it from this part of the trusted node to here where it's needed, but there's going to be some point, even if it's on a chip somewhere, where that key is now available, whether you do post-quantum or not. So I think for me, I don't know. I certainly think that post-quantum has a role in the authentication side, and maybe you can do post-quantum to get that key from one end of a box to another box that might be down a corridor in a BT exchange or something, possibly. But I think for me, it's more about putting the boxes in a secure, locked area and only have certain access to certain people, as we do anyway, to be honest.
Yeah, okay. Thank you.
Andrew, if I may kind of add on this one with regards to the PQC, I think there are two different problems here. One is the thing about the channel itself. So channel, we're talking about DWDM and also the QKD, the quantum key distribution. And that, regardless of whether you have PQC or not, that will stay. And that is where a company like BT or AT&T, which provide this pipe, if you like, and that's where the QKD will come in place. Regardless of that, PQC can still be used, because the purpose of PQC, which is a software-based approach, is to actually make it harder for the key to be deciphered using the power of quantum computing. So regardless, these are two separate things, and they can be applied to complement each other. Andrew, would you agree to that?
Completely agree. Yeah. I mean, so if you think, in fact, more than that, if you think about how this would be implemented, the equipment that you use, so this would be Ethernet encryption equipment, for example, already has these algorithms built in. So why would you switch them off? That's kind of their bread and butter. Now, at the moment, I guess most of those algorithms will be based on something like Diffie-Hellman, but in the future, they will have post-quantum built into them. I'm not suggesting for one moment you switch those off. What I'm suggesting is provide an additional layer of key generation externally via QKD, just to supplement, if you like, and then you get the best of both worlds.
I see that there are many other questions, but I want to be respectful of Andrew's time because I know he's stayed up late to talk to us. Maybe we'll just ask one more question. What is the highest key exchange rate over the fiber?
Entirely distance dependent. We're seeing typically, and this is now bits. So we're seeing hundreds of thousands, more likely less than 100,000 bits per second. So then you have to distill that into keys. So now the keys will be coming in 512 or 256 bit chunks. So you can do the maths, but yeah, it's of that order. And it's not enough key rate to do one-time pad for the complete data channel, because the data channel is terabits. Okay, so you know, this is the bad news. You're not going to be able to use QKD directly on the data. You have to use it to generate keys, which are then used to encrypt the data using something like AES.
Okay, thank you so much, Andrew. That was fantastic. We've never had that many questions. So thank you again, and thank you everyone. Hope to see you all again in 2 weeks.
That was great fun. Thanks, guys. Take care.